Good day and welcome back for the fourth part of our discussion on differentiating exponential functions. In our previous videos, we've actually covered the relevant material, and we're in a perfect position to kind of recall the key facts or properties that we've discussed and do some additional practice. And also hopefully allows us to reinforce and remind ourselves of some of these key properties from Calculus 1 with differentiation and integration that we've used many times in the past, and we will also use frequently throughout this semester. So when it comes to an exponential function, it has this form a to the x, where a is the base of the exponential function, and we restrict it to be positive. Graphically, there's really two cases of interest for us to consider. When a is between 0 and 1, the exponential function is decreasing and roughly, looks something along these lines. And note in this case, the y-intercept is 1. Similarly, when the base value for the exponential is larger than 1, we get an increasing exponential function, which also has a y-intercept of 1. And you can see a few key limits that I'm not going to write down, but in the case of a being between 0 and 1, as x goes to infinity, the function goes to 0. As x goes to minus infinity, the function blows up to infinity. And similarly, if you look at the graph of a to the x, when a is bigger than 1, the limit as you approach infinity is infinity, and the limit as you approach minus infinity would be 0. And a particular case of interest for us is when the exponential function is e to the x, where recall e is this number that's approximately 2.71828 and so on, but the key thing is it's bigger than 1. So it falls into this second case. That immediately tells us two limits of interest related to e to the x. As you approach infinity, you get back infinity. And the limit as x approaches minus infinity of e to the x is equal to 0. We also developed some differentiation formulas related to the exponential. First, we had this more kind of generic formula. For a to the x, its derivative is always going to be a to the x f prime of 0. So it's in terms of f prime of 0, which is a number, and in future sections we are going to determine this number a bit more precisely. But for now, the key case of interest is e to the x. It is its own derivative, and it is its own antiderivative, up to adding a constant. And taking it a step further, we know that we frequently will encounter exponentials of the form e to the kx for some non-zero constant k. By the chain rule, the derivative of e to the kx is ke to the kx. And thinking about undoing that, or maybe using a substitution, the antiderivative of e to the kx is simply 1 over k e to the kx plus c. So let's go ahead and do a bit more practice. I would encourage you, for the derivative and the integral that remains, to pause the video, give yourselves 3 or 4 minutes, and work through these two examples. And ideally, as we practice more and more, these are just going to become quicker and more efficient. For this first example, we've been asked to differentiate, and note it's a composition. You have the square root on the outside and 1 plus 3e to the 5x on the inside. This requires the chain rule. We take the derivative of the outside function, and the derivative of the square root is 1 over 2 square roots. We substitute in the inside function, and then we multiply by the derivative of the inside function. And I know it's always tempting to do this all at once, but I don't think it's ever an issue to show some extra steps and make sure we don't make silly mistakes. So we have this one derivative we need to now evaluate. The derivative of 1 is 0. plus we have 3 times the derivative of e to the 5x, which is 5 e to the 5x, as we noted above. And we could leave it in this form. I'm going to take it one step further and just make it look a touch more convenient. 15 e to the 5x over 2 square roots of 1 plus 3e to the 5x. For the definite integral, we are going to want to use a substitution. So we choose u to be an inside function. And note there's really only one choice for that inside function. Square root of x is inside the exponential, and it's also in the denominator of the fraction. So let's see what we can do. Du, as we just mentioned, would be 1 over 2 square roots of x. Then we throw on our dx. And if I slightly rewrite this integrand, just to make it more convenient, we have e to the square root x times 1 over square root x dx. So now we hopefully recognize quickly, we see our u, and not quite du, this is 2 du. So we now have our integrand written solely in terms of u, and 2 is a constant, which we can pull out front. But recall, whenever we evaluate a definite integral with a substitution, we must change our limits of integration. Our lower limit of integration, x equals 1, becomes u equals 1. Our upper limit of integration, x equals 4, becomes u equals the square root of 4, which is 2. And now we have a very quick and efficient integral to evaluate. And antiderivative of e to the u is e to the u. We substitute in 2, we put a minus sign, we substitute in 1. Let's now look at one more example involving limits before we move on to explore properties of the natural log function. So for our final example, let's see if we can determine the limit as x approaches 0 from the right of the function e to the 1 over x. And it turns out that this is something we really have to think about from a more graphical perspective. So let's just first think about intuitively what's going on. As we approach 0 from the right, we need to think, what is 1 over x doing? Well, graphically, 1 over x, this reciprocal function, is hopefully something we are familiar with, and it looks roughly like this curve. So if we would like to know what is the limit as x approaches 0 from the right of 1 over x, we're thinking as we substitute in values close to 0, but on the right-hand side, what are those function outputs doing? Well, they're approaching infinity. So note, 1 over x is approaching infinity as x approaches 0 from the right. And we even know what happens to the exponential as you approach infinity. The graph of e to the x would look something like this. And above, this is 1 over x. So as we substitute in values that are getting bigger and bigger, i.e. going to infinity, the graph of e to the x is also going to infinity. So we can say this is equal to infinity because the limit as x approaches 0 from the right of 1 over x equals infinity, and the limit as x approaches infinity of e to the x is also infinity. So I think the most difficult part in a problem like this is actually including that justification as to why we get infinity. So we've now finished our discussion on differentiating exponential functions, and what remains is for you to spend some time practicing. So make sure to go through the suggested problems, focus on understanding what is going on, and also use this as a really good opportunity to review some of these basic calculus properties that we encountered in Calculus 1. In our next video, we will move on and discuss properties of the logarithmic functions. So stay tuned. Take care.